Welcome back. So this is part 2 of week 4, module 1, and we're going to start now with reviewing sample size for proportion. So this is when we have categorical data, when a chi-square test would be appropriate. So again, as I just mentioned, chi-square test is used for categorical dichotomous data. An example of when you may use this is for instance, if you had survival data. So the same steps that we talked about in part 1 would be appropriate here. You're going to state your hypothesis. Is it one-sided or two-sided? Determine the effect size and variability in the terms of proportion, and then you're going to set your alpha and beta. So listed here then is the equation that we use for estimating sample size for proportions. And P then stands for the proportion. So the mean proportion is the average of the baseline proportion and the treatment group proportion. So P0 then is that expected success, that proportion in the control group or that baseline group, and then P1 is that proportion in the treatment group. So sample size is maximized when that mean proportion is 0.5. So if you plug in 0.5 for the average response rate here, then the equation is listed here as far as 4 divided by that difference between the control and the treatment group squared. So now we're going to work through, just like we did for the t-test, we're going to work through an example here on the slides. So for a proportion example, we have a researcher who wants to determine the necessary sample size to detect a 20% difference in the treatment success with a new antidepressant versus placebo. So our alpha, again, assuming a two-sided test, we're setting this at 0.05, so our gold standard. Beta then is 20%, meaning our power is 80%. So the baseline rate of treatment success with placebo, based on other studies, is around 40%. So with a 20% difference, and we want our new drug to be better, we expect a rate of success with the new drug of 60%. So then working this into, here's our equation. And if we're using that, the assumption of the mean P is 0.5, then we can use this equation, and you can see that our control, our placebo, is 0.4, and then our treatment group is 0.6. So 0.4 minus 0.6 squared gives us about 100 subjects in each group that's necessary. So then I just want to go then and do this again with our JMP calculator. So let me pull that up again. Again, remember, within JMP Pro, we're going under the Design of Experiment tab. Sample size and power calculator is the last choice there listed when you click on that tab. So I'm just going to click on that. All right, so again, now we have proportions. So this is the two sample portions for what we're determining. So we're going to click on that calculator. All right, and I'm going to pull my slides back up just so I can see. Let me go back up to the equation so I can see what to plug in. All right, so in this case, again, our alpha is set for us 0.05. We know that our proportion 1 is 0.4, so this is our placebo rate. We're expecting a 20% improvement for our treatment group, so we're setting that at 0.6. We want two-sided. The null difference in this case, so don't confuse this because remember in the last example we only had one input up here, and then down here we had to put that difference that we expect. This is not delta in this case, all right? So in this case, the null difference is always going to be at 0. All right, so we're trying to determine our sample size per group here. And then we want our power of 0.8. So then we hit continue to see what this has given us. All right, let me go back down here, compare it to what we have, pull this back up. And what you can see is that we need 97 per group with our proportions calculator. And this is very similar to what we calculated by hand as far as getting 100 subjects in each group. All right, and again, this is exactly what I'd like you to do for your homework, is do it by hand with the calculation, and then I want you to also do it with the sample size calculator. All right, so oops, that's not what I wanted to do. All right, back to our slide deck. Some other considerations that I wanted to point out with regards to sample size. Non-inferiority studies, which we haven't talked about yet, but we will later in the semester. Keep in mind that for these types of studies, the hypotheses are actually swapped in this case. So typically everything is based on the null hypothesis. In this case, the hypotheses are backwards with regards to non-inferiority. So in this case, beta is often set much lower. Survival analysis, we can actually estimate sample size here just like we did for the chi-square using the proportion alive at any point in time. A good rule of thumb with regards to regression analysis is that you have 10 cases per independent variable. So keep in mind though, so a lot of times for the projects we do multiple logistic regression or multivariate analysis, that this would not apply because we always base our sample size and power estimate on the primary, and that is typically something that we do in the secondary. So in that case, this general rule of thumb would not apply. But again, if your primary was some type of regression, then this would be a good rule of thumb as far as 10 cases per independent variable. And then always keep in mind the dropout and that you need to increase the sample size by a factor of those that are going to be lost to follow-up. So what do we do then if we have a fixed sample size? So this would be the case with regards to secondary data analysis. So when we have a data set where the number of subjects within that data set is already set, and we have no control as far as enrollment or anything like that. It's just a set number that's there, and when we filter by our research question to get it down to our study population, might even be less than that. So we are set with a standard population, and then based on that, how much power do we have and to detect a certain difference between the groups is what we're trying to determine. So this is a very debatable topic among the clinical research faculty because, as you know, a lot of the studies, a lot of the projects that we do are based on secondary data analysis. So we use a lot of the publicly available databases. So we have no control over how many are in these databases. So typically, a sample size estimate is appropriate when you're designing a prospective study. In this case, we debate back and forth as to whether sample size is appropriate. My argument there is that as students, and with regards to this degree program, you need to know how to calculate a sample size estimate for a study. So that's why it's necessary there. But it also is appropriate in this case if you would prefer to work backwards and estimate the power that you would have with your study. That's typically fine as well. But regardless, either way, you're going to need to know the difference that you expect to see between the groups. All right, so whether you start and try to estimate the sample size of what you would need to be powered, or if you work backwards and say, there's this many in the database, I'm estimating at a difference between the groups of this would give me this much power. Either way is appropriate, and for my groups and for this class, I will accept either way. And then it will all depend on who your advisor is for project. So again, when I say my groups, I'm talking about my groups for the research project. All right, so let's work through this. So again, we're working backwards to estimate the power with various effect size. So how small or big of a difference could you detect with this defined sample size? So our example here is Dr. Smith has 250 patients in his clinic that has records that he can evaluate. He wants to determine if there's an association between gender and 5-year survival among his patients. So what difference in survival could he reasonably detect between the two groups, assuming a two-sided alpha of 0.05? He estimates the 5-year survival for men to be on average around 60%. All right, and you can see that I have these I've already worked in there with regards to the calculator, but I'm going to go ahead and pull them up again so that you can see. So you can see I already have, let me go back again. I already have my proportions. I'm going to go back so it clears everything out. I guess it doesn't clear it out, but so here I have my proportions. So I know that proportion 1 for men is going to be 0.6. All right. What I don't know right now is the two proportions. All right, so that's what I'm going to have to estimate. All right, this null difference again is 0. We know the sample size in this case, so 125, so 250, so 125 men, 125 women is our assumption. We're trying to determine how much power we would have. So let's see here. In this example, let's say that women have a 5-year survival rate of 80% compared to men. So this will be a 20% difference. So let's put in 80% here. All right, see what we get. And you can see we have 93% power here, 94% power. All right, so what if we varied that a little bit more? Because remember, we want 80% power, correct? So let's say we put this at, again, deleting our power, 0.7. And you can see there we get a power of approximately 38%. So that's not what we'd like there. All right, so let's vary it again. So what if we put in 0.77? Again, deleting our power. And there you can see 83%. Oops. 83% power. All right, so we have 83% power to detect a 17% difference in survival between men and women. So a great way to present this then, or with any sample size, is to actually portray this in a table. And you can see that's what I've done here in this table for this example. So we had 125 per group. The estimated survival, that's in this column here. The estimated survival was men for 60. For men was 60%. We varied that for women. All right, and you can see here the difference between these two is our delta here. So here we have 20%, here we have 10%, here we have 17%. And then based on each of those survival estimates for women, this is how much power that we have. All right, and you can also do this. It doesn't necessarily have to be just for power. It's a good idea to present this also for sample size. If you're varying your power, so between 80 to 85%, or you're varying your effect size, say between 5, 10, or even 10 to 20%, you can present it in a nice table like this. So this is something that's important with regards to moving into project that we like to see within your study. All right, so wrapping things up then, keep in mind that it's usually easier to estimate sample size with the simpler methods that we went through with regards to Module 1 here, so including chi-square and t-test, so it's much easier, simpler method to calculate sample size. Just some general rules. Again, our 80% is our gold standard that we would like to have for all studies in order to consider to be able to detect a reasonable difference between your groups. Keep in mind that if you have continuous data, this will allow for smaller sample size compared to categorical data. Paired measurements also require smaller sample size, and this is because you're comparing the subject with themselves, so they're serving as their own control. So this is removing that baseline between subject part of the variability of the outcome variable. All right, so there's no between subject variability there with paired measurements. More precise variables also yield smaller sample size. So this is because precise variables decrease the variability. Also, if you have unequal group sizes, you can gain in power when the size of a group is increased to twice the size of the other group. So this would be the case like if you had twice as many controls than cases. And then also if you have a common outcome, so an outcome that occurs more often, there is more chance to detect its predictors. This is also going to increase your power of your study. Sorry, I forgot to go to full slides there. So then here on this slide is just some sample size calculators. Again, I would recommend that you stick with the sample size calculator, power calculators within JMP that was reviewed in this class and also reviewed in Dr. J's class. There's also the DSS calculator that we have used previously. The one caution with regards to this is the sample size calculator. There's an error with regards to it. It always assumes one sample rather than two. So if you do use the DSS sample size calculator, make sure that you also check it with the statistical power calculator. So both of those are available within the DSS toolkit if you go to that link. And then there's also some multiple regression and other special situations available at this link here that I've included, and then there's also a power calculator that you can download for free from the CDC with regards to that information there. So what do you do when you don't have enough information to calculate a sample size? So you want to make sure first that you've done an extensive literature search. We've also mentioned previously that you could conduct a small pilot study. Also, think about what's going to be clinically meaningful with regards to your study. So a good rule of thumb as far as clinically meaningful difference is around 10 to 20% if you can't find anything in the literature. Also, you can dichotomize your outcome variable. This will help. And then also, educated guesses about the missing elements. Keep in mind that very few grant reviewers and medical journals will accept any arbitrary decisions, though. And then what to do if things don't go as planned as far as your sample size. You can always conduct a post hoc power analysis. And what this means is just doing a power analysis after the fact, so after you've already done the study, to determine how much power you actually did have in your study. And that concludes part 2 of Week 4, Module 1. Thank you.